I want to thank the organizers for inviting me. They invited me early enough so that I could fix myself an objective to finish a work that I had in mind since a few years, but I put aside. So it's on archives since not a long time. So I needed to split it into two parts. Okay, so part one is self-similarity. This one is broken. Self-similarity, aperiodicity, and minimality. In the second part, so when you want to show something is self-similar, sometimes you need some combinatorics, test many cases, and this takes pages. So this is why I decided to split it into two, because minimality. We don't need to read all of this to understand the second one. So that's so the second paper is the dynamics of an aperiodic computer chip. Okay, so we will present this today. So before starting, I would like to share a question that for me was the motivation for looking into this. So it's kind of a reverse engineering kind of question. Reverse engineering. Let's hope I don't make a mistake how I spell this. So the previous talk was great. Thanks, Guillaume, for explaining the Gary tile set. So these tile sets are computing something, right? Multiplication by 2, by 2/3. There's such an orbit of that map G or F equals, it's a B-infinite orbit, and this allows us to build tilings and understand them. Thank you for the water. So the question I was wondering was the following. So given a set T of Wang tiles, suppose it's an aperiodic set. So it tiles the plane and always non-periodically. Can we replace the labels by values satisfying equations? And then you use the equations allowing to prove non-periodicity in 10 lines. So the paper by Carey and Kulik, both in 96, tells us, yes, this is what they have done. They provide the values for the Wang tiles, and they prove, look, it's not periodic. In 10 lines, page 2 of the paper, the proof is done. It's quick. It's not 60 pages or 80 pages proof of aperiodicity that we have seen for the mono tile. Like the hat, it's 80 pages. 10 lines is nice. So can we always do this? For instance, for Jean-Noël Rao, can we do this? So the reason why I believe we can, so I don't have time to present this. I came in Marseille in September, gave 2 talks, 1 hour each, to explain that. I will not be able to explain it again. But macroscopically, I know that what the Wang tiles are doing, right? The tilings are explained. You have a torus here, whose lattice is given by irrational values. You have a lattice. You put on top, the torus is partitioned into labels. Any position of the lattice on top gives you a configuration, and these configurations are valid the tilings by Jean-Noël Rao. So macroscopically, I understand what's happening. the tilings are computing the orbit are of +1 vertically and +1 horizontally on a torus whose length are irrational. So it makes sense to say, well, if the tilings are doing this, maybe the tiles are doing a computation of +1 horizontally and vertically. We need to see those labels as arithmetic values. So the question is still open, okay? But what I want you to understand today is something's wrong in this question. And what is it? Is this word here. Values. This is wrong. You want to replace this by the word vectors. So let's start the talk. Definition of the set of tiles. So you take n, an integer, and then we will define our labels. So it will be vectors of, we'll denote them v0, v1, and v2. Non-negative integers. I want them to be non-decreasing. So these are the following inequalities. And I want v2 to be at most n+1. Okay, and I want something more. I want v1 to be at most 1. On this set, I will define now a map that I call theta n. So this will take 2 inputs in Vn. So the first I will denote it with u0. This takes too much space. u0, u1, u2, and v0, v1, v2. So this, I map it on some three-dimensional vector with possibly negative entries, okay? So I will write it like this. This will be R0, R1, R2. And I want R0 to be always equal to U0. And then here there will be cases. So R1 will be either V2 minus n or 1, depending on the value of U0. So this is if U0 equal 0, and this is otherwise. And R2 will be, there will be two possibilities. So it's either V1 plus U0 if, this time, if V0 equal 0. And otherwise we will give it the value U2 plus 1. So this is where we have the plus 1 happening, okay? Otherwise. But sometimes it's subtracting minus n, right? So subtracting. So this map theta n, we will use it to construct what I call a computer chip. So what is a computer chip? It's something.
Why did you consider this definition?
This is a. It's a good question. I built it using reverse engineering.
Of John Del Rao?
No. Of something else. You will see. So this is a chip that will receive inputs on the left and on the bottom. So I put 3 lines, not for nothing, because we are vectors here. So here I put U, and here I put V. Okay? I want this chip to compute theta n. I will write it on it. This is my theta n chip. So here I want to output theta n. Let me try to write to the bottom. Theta n of UV, like that. And on the top, I'll erase that here. I want to output theta n of VU. So this is a theta chip. So my claim today is that this is an aperiodic mono chip. There's a monotile since last year. This is a mono chip.
So is that for a fixed n?
It will be for all n. For all n, this will be a aperiodic mono chip.
So n fixed?
Yes. This is exactly what I write in the paper. We cannot say it's a monotile because we need to look at all the different inputs. I'm just cheating a little bit. We go in that direction. So what I want to do with this chip, I want to construct clusters. Okay, I want to plug them to each other. So I want you to have this in mind. You have this chip and you plug it with itself. And you construct arbitrarily large clusters of these chips. And we will show that these are non-periodic and arbitrarily large such cluster exists. That will be the result later. So if you plug the chip with itself, this forces you the output to match the input, right? And this is what we'll define because we have a subtraction here. This can give negative entries, so this will not be in Vn. So we need to restrict a little bit. This will define our set of Wang tiles. Okay, so the different instances of this chip defines a set which I call Cn. So U, V, theta n of UV, theta n of VU, such that UV is in the set and the output as well. Okay, so this is a set of Wang tiles, okay, the instances of the chip. And maybe I can define this as well. Omega n will be the set of, I use double, of valid configuration over these set of Wang tiles, okay? So we will now explore these tiles, but before it's good to make a few notes. So the first I suggest to look at is when the vectors start with 1. U1, U2. Ah, yes, thank you. That was missing. V1, V2. So I will denote my vectors as words. So I remove the... So if you look at the formula, what does this do? It returns this. 1, 1, and U2 plus 1. Since we have a lot of plus 1 involved, I will denote this by 1, 1, U2 bar. So bar for me is plus 1, okay? When I underline is minus 1, but I will not use it. So over is plus 1, okay? Overline. And then another one that I want to do with you is the following. So it's 0, U1, U2, 0, V1, V2. What does it do? you can check, but I claim it's 0, V2 minus n, V1. So notice in particular, in this case where the vector starts with 0, 0, this does not depend on u. It depends only on v, okay? So, I have a gift for you. I counted 64 participants in the list, so I printed 64 of these. So I give a talk on the board, but I do need pictures. Please, Pierre, give this to everyone. Give a copy to everyone.
But what is the minimal value of n when this is makes sense? 1?
1, yes.
And then how many tiles you have?
We will go in that direction right now. We will answer this. Now we will explore what are these tiles. Okay? So one of the tiles are those such that the input starts with 1 in both. So I will denote this by 1,1i and 1,1j. So if you look at what I wrote on the notes, the output, I made a mistake here, is 1,1i plus 1 and 1,1j plus 1. So these belong to C that are instances of the chip. I call them white tiles. Take some color for the next one. So B and prime, there will be a reason why there's a prime, are those such that it starts with 0, starts with 1, the U and V. There will be 4 of those cases, 0, 1, 0, 1, 0, 1, 0, 1. There are 4 cases, okay? The blue, I call them the blue tiles, because I associate color blue to the fact that the input starts with 0, 0. And since the output here is 0, 0 as well, I draw an horizontal strip of blue color here like that, just to differentiate them from the other one. So these I call them the blue tiles. So these are instances of the computer chip. And then you have the yellow. I associate 0, 1 with color yellow. And since it starts with 0, 1 here and here, I put a yellow horizontal strip just to distinguish them from other tiles. So these are my yellow tiles. And these are instances of the computer chip. And then you have the green tiles, which mixes yellow and blue. So this one has blue on the left and yellow on the right. So what does yellow plus blue do? It gives you green. So there is an overlap of the blue and yellow, which I call the green overlap. So these are the green tiles, okay? So these green tiles are instances of the computer chip. And then you have this. Yellow on the left, blue on the right. But these tiles, we don't like them because they are against the system. We call them anti-green tiles. But still, they are instances of the computer chip. And then the remaining ones, we'll call them the junction tiles. Here I'm reusing the vocabulary of Moses, the paper from the end of the 80s. He's using junction tile also. So for the same reason, it makes sense to call them like that. So there are 9 junction tiles. The input here is 0, 0 at the bottom on the left. And as we have seen here, in this case, the output depends only on V. So V is here. So in this case, it's like the input goes directly here because it does not depend on U, except the fact that U starts with 0, so it does depend a little. So this is blue to blue. This will be a yellow to yellow. And this one is a yellow to blue. So let's put both color. I don't put green because when I say green, I want you to think about this, not the junction tile. And then you have the symmetry of that. So here you have the blue, you have the yellow going up, and then you have the yellow to blue. And then for all of these three choices, you have a junction tile, okay? Okay, so now we can continue. We have done.
So why don't we like the green?
It's a good question. We'll come back to it in a moment. I will move this one up. So can you tell me while this is moving up, few tiles are missing? Can you tell me? We don't have there are remaining tiles in the CN. Which one? It's an easy question. You need to be able to. So this I have not written out, but these are instances of the computed chip. So which one are missing? Okay, you have enough time to think about it. There are images under the symmetry, right? So the yellow, you flip them. The green, you flip them. And the anti-green, you flip them. So these are also instances of the computer chip, where, just to make the notation clear, when I flip a tile, I flip it like that. A, B, C, D, okay? So we have these, and nothing else. So Cn is the union of these subsets. So just a case analysis, and okay, we have done all of the cases. That's it. And then we will go towards the previous questions. So in a valid configuration, I will denote it W in Cn. In omega n. The following tiles do not appear. Which one do you think? Those who are against the system. They don't appear. You cannot surround them by arbitrarily large surrounding. They are against the system. They don't want to fit. Okay? And some other tiles as well. And this is why I put prime here, because we do need to remove from those sets some tiles. So last week I practiced my talk, and one of the person was able to guess one of them. Maybe you or someone did, or here as well. I give the answer. So the last blue tiles, there's a problem with that tile. Omega n is the set of valid configuration. Did I wrote it there? Is the set omega n is the set of valid configuration. Is it okay? So this one is easy. This one is hard. This one is easy to show because you don't see any tiles with 0, 0, n plus 1 as input. There's nothing else to put here. You can check, but there's nothing matched here. Right here, there's nothing to put. So this tile is useless. There's another one which is useless, but this one is not easy to show. Well, it's not difficult, but not easy. Is this one. So where the input starts with 0, with these values. So let me put color. So it's yes, it's a blue to blue here, and a yellow to yellow here. So this one, you will not see it in any configuration. And I should say that their image under the reflection will not work as well, okay? So now we can define our set, Tn. Let Tn, the instances of the computer chip, which are the remaining one. And we will count them, so that will answer the question of Sasha Shen in front. Let Tn be the remaining set of n square white tiles, 2 times n blue tiles, plus n yellow tiles, plus n plus 1 green tiles, plus 7 junction tiles. So this is equal to n squared plus 6n plus 9, which is equal to n plus 3 square tiles. And now you see the images that I gave you. You see a square of tiles of size n plus 3 times n plus 3. So these are the tiles for when n is equal to 1, n is equal to 2, n is equal to 3. So when n is equal to 1, you get 16 tiles. You can also replace by n equals 0. In fact, it works. You get 9 tiles, but they tile periodically in a trivial way. So you need to exclude n equals 0. So the first theorem we can show, well, it's not I don't know. It's very easy to show. We will make the proof, but it's still interesting. So is that when n is equal to 1, T1 is the Hammond set, or is equivalent to, is equivalent to the Hammond set of 16 Wang tiles. So let's make the proof. So if you replace 1, 1, 2 by 1, 1, 1, 1 by 2, 0, 0, 1 by 3, and then 0, 1, 1 you replace by 4, 0, 1, 2 you replace by 5, and 0, 0, 0 you replace by 6. That makes the bijection between this set of T1 and the Hammond set, which you can find in the book of Grambon and Shefford at some pages, which was deduced from the L-shaped Hammond, There are some interesting questions in that direction as well. So, in the time that remains, I will state theorems. We use the other board. This I want to go up. And this one down. Let me take some water because Okay, so now we will discuss the self-similarity. So this is what was isolated in part 1 paper, okay? Takes more pages to do. So what you can show is that for every n integer, omega n, which was already defined, is self-similar. So what do I mean by this? Sorry, I will introduce stuff here. Is that omega n is equal to the image under a substitution of itself. So of course when you write this is false because you need to shift just a little because maybe the origin is inside of the image of some letter, right? So this equation is false. And I'm sorry, I'm using a notation which I don't like, but I forgot to change it before I post it on the archive. So to be consistent, I'm doing this with sigma here. So it's not the topological closure, but just the closure under the shift. So just the union under some finite amount of shift. So this is what I mean by self-similar, but by definition of self-similar, it's not enough to write this when you do this in 2 dimensions. You need to also say, well, omega n is expansive in all direction. Otherwise, it's too easy to do, and I don't write it here. But what you also have about this substitution, omega n, is it's recognizable. It's a recognizable 2-dimensional substitution. So it sends the letter on blocks which will be either n or n plus 1 for the width, and the height will be n or n plus 1. It's just so that you have in mind what kind of substitution it is, but it's the kind of, it's rectangular shape, but it's not constant shape, constant size. So recognizable means it's there's a unique way of substituting, and I will give just a little bit the proof and just a proof sketch here because this takes many pages, of course, which will illustrate what is meant here by recognizable. So if you look at the tiles, and you have on the paper I gave you at the verso a typical tiling with the set T3. So you see that those tiles, they will match edge to edge to form rows of color and column of color. And at the intersection of a row of color and a column of color, you have a junction tile. And it's a if and only if. Each time you have a junction tile, it's because here you have a row and a column of color, okay? So your tiling can be decomposed using the junction tile. So here you have a junction tile, I will call it J here. And maybe here you have another one, the next one on the same row, and below you have another one here, and here again. So the position of those junction tiles are a Cartesian product of 2 sets, and these 2 sets are increasing by in both ways. You know, they cover. Well, the distance is always n or n plus 1. That's the first thing you can show. So there's always one on the left, always one on the right, always one on the top, always one on the bottom, at distance n or n plus 1. So what do? This gives us a natural way of decomposing our tiling like that. At the left of each junction you will cut everywhere, and you will do the same below of each everywhere. So this decomposes your tiling into blocks, which I call return blocks, because you know it's similar to the vocabulary of return words in 1 dimension. They call it return words. Let's call them return blocks. So do you agree with me that there's a unique way of decomposing any tiling like that, right? So this is what we mean by recognizable here, okay? And then the next step, I like it very much. And this is why I want to show this proof. Well, now before that, I need to say something else. You can show that there exists a map which I call tau n from Vn to Vn star. So from a vector to words of those vectors, and the length will be always n or n plus 1 of these words, such that the set of return blocks is equal to applying this tau map on Wang tiles we have seen before. So A, B, C, D, such that these are Wang tiles in Cn. So the return blocks are instances of the theta n chip. And for me, this is kind of fabulous or mystery or some magic is involved, right? Because there's no reason why this happened. Could have been Tn, I would have been happy, but it's Cn. So let me put an exclamation mark here, because for me this is kind of magic. Or some explanation can be done that I don't have. I just noticed it's like this and I find it very nice. So those return blocks are instances of the computer chip, meaning some of them will be maybe the NC green or the last blue tiles. But if you start from a configuration, then of course it will not be an NC green and it will not be the last blue tile and so on, right? It will just be the return blocks corresponding to Tn. And then you have the self-similarity here. This is what defines this map, omega n. You map this to this. Of course, you need to fill it in, but there's a unique way of doing it, and that gives a substitution. So, as a corollary of this, we get, using well-known argument, that omega n. These are words, so these are always of length n or n plus 1. And I can give you more details on this if you want.
But are the return blocks squares or?
No, return blocks, all possibilities happen here. So the junction tile will be mapped on n plus 1 times n plus 1. The white tiles will be set on n times n. And the vertical stripe or the horizontal will be n times n plus 1 or n plus 1 times n, right? So all of them are possible. Question, yes?
So return blocks are locally allowed return blocks?
Yes. If you look at all of the locally allowed, you get that.
Will be like only those corresponding.
Yes. But when you want to do the proof, you don't want to go to the infinity. So you just look at what can happen here, and then you realize that these are exactly what can happen. Yes. So from this theorem, you have this, right? Because you use the substitution to apply it over and over and over again, and then you get at least one configuration. So omega n is not empty. And since you have a recognizable substitution, which is expensive, then it's also using the same argument as the red square in the previous talk. It needs to be non-periodic, all of the configuration. So this we have as a corollary, and then you can show more. For every n, the substitution is primitive. So, which means all tiles appear with a positive frequency, which you can compute. And I can give you more information on the substitution, but I suggest to postpone it at the end because I have priority things to show you before going into details here. For every n, so you can go one step further in that paper because you use the substitution to prove this, but you can show that it's minimal. And here I could add an exclamation mark because Carré-Kulik is not minimal, Jean-Del-Rao is not minimal, Robinson is not minimal because you have those fault lines. Many times it's not minimal. Often this one is. So this is why this set is nice compared to others. It has a very nice property. And this would be useful to make theorems after because you just need to show, well, I have a subset. It's closed for the topology, closed for it's shift invariant. It's minimal, then we have equality, right? This is what happens in the second paper. So now I would like, so up to now it's not like Carré, right? Because Carré is not substitutive and the way metallic, these Wang shifts are substitutive. So there are still two isolated worlds, right? The Carré-like and those ones. What I want to show now is that Carré is not alone in his world. So, I want to construct configuration. Of valid configuration. So this is from part 2. So take beta, a real number, such that when you subtract it with its inverse, it's an integer. So, of course, this you can translate it, so let me do it for you in other way. That is, beta is a root of x squared minus nx minus 1. So it's a quadratic integer, but it's a, let me write it. So if you try to solve the formula, you get this. But more interestingly, if you write it down in constant fraction expansion, what you get those such that the period is 1 and it's n, okay? These are the one. So, according to Wikipedia or the online encyclopedia or integer sequences, these are called the nth metallic mean. But other names, maybe I can just take some time. They were named, other names were given to them. For instance, sometimes they were called silver means, okay, with an S here, silver means. So this is if you look in the book of Schroeder in the early 90s. And then the name metallic was given by the Spinadel in she has many papers, but one of them is 99. But she was using minus px minus q. So it was always minus, but some variable. She was including more of those metallic in this set. So this is why in the book of Michael Bakker and Uwe Grimm, they rather call it noble means. as a subset of those, because noble means when it's -1. So this is Michael and Huey. But noble was a word used already in the appendix of that book for something else. For those in the orbit of golden mean, when you act by the Mobius transformation. So those that finishes by 1, 1, 1, 1, 1. And other people rather call them just quadratic Piso number. But these include the case where this is +1. Anyway, I decided to follow what Wikipedia says and the online encyclopedia of integer sequences. And I'm using this for the title of the paper. This is why I wanted to justify a little bit more. So now, using beta, we are going to construct tilings with this map. So it's a map from the unit square, 2 vectors, and to xy, you associate it with the following vector. So you will take the floor part of y minus beta minus 1 plus 1, floor of that. Then you will take the same, and you will add beta minus 1x to it. So plus y minus beta minus 1 plus 1. And then the last, you will replace this beta by beta minus 1 by beta. Beta x plus y minus beta minus 1 plus 1. Take the floor part, and maybe you want to transpose it because all of my vectors are line vector for up to now. Okay, so you define this. So for n equal 3, let me, this is what happened. So this is the unit square, 0, 1, 0, 1. And this is beta minus 1, this line here. So when y is above, the first entry of the vector is 1. And when y is below beta minus 1, the first entry of the image of the lambda tree map is 0. Okay? And then, if you look at the first the first two, you get that. 0, 0, and then 0, 1. So, well, you can do the math, right? But below this line, it's 0, 0. And above, it's 0, 1. And above this horizontal line, it's 1, 1. And then the last entry gives you, I will go fast, but it's 1, 1, 1, 1, 1, 2, 1, 1, 3, 1, 1, 4. Here you got 0, 0, 0, 0, 0, 1, 0, 0, 2, 0, 0, 3. And then you get 0, 1, 1, 0, 1, 2, 0, 1, 3, 0, 1, 4. So you get that, okay? You just compute and you see this. So you get the following lemma, because what we have seen there works in general. The image of this map is in Vn.
So this is independent of n?
Yes, you fix n.
Oh, theta.
This is an integer. It's the same as before. Beta depends on n, yes. So these are all non-decreasing vectors, and one of the vectors does not appear. It's the 0, 0, n bar. Because you see, it would be here, like it's just a singular point, so it does not appear. And this is the color of the last blue tile, which is not necessary, right? So now you do this. I have 2 theorems to state. I hope I will have time to state them. You define a rotation by beta on the unit circle using the often used notation of the curly bracket. So curly bracket of x is x minus the floor part. So this gives you a rotation by beta on the unit circle. And then you can state you can construct configuration using that. So for every n, for every xy starting point in the unit circle, the following tile, which I will call Tijxy, and here I'm using on purpose the notation of the paper of Carey from 2016 to show the existence of tiling for his tile set, where you give the following labels using lambda n. So lambda n of rotation by beta e times on x, and rotation beta on y j times. And then you do the same here, but just swapping the two entries. So lambda n rotation j times of y, and rotation beta time e times on x. And then you just, on the left and at the bottom, you just make the choice which is consistent to make a configuration. So you just reduce I by 1 for this one here. So R beta I minus 1 of x and R beta j of y. And here you reduce j by 1. So lambda n R beta j minus 1 of y R beta. Okay, so this for now is just, okay, I constructed the Wang tiles. We see it will be compatible with the tiles around it. And this allows you to construct a map. Okay, sorry, the sentence is this tile in fact belongs to Tn. Okay, and the map, and this is not easy to show, and this is where you will use the fact that beta times beta minus 1 is minus 1, and the sum of the subtraction is n. This involves everything we need on beta to show this. And then the map, and this is easy, the easy part, depending on xy, which to z2 you map to Tn, and you affect at the position ij the tile Tij xy is valid. So I would just write it quickly like that. It's in the Wang shift. So this follows a statement which was known for Carey, okay? But where here, we don't have multiplication involved, we have rotation by beta, or beta minus 1, because we will see this just after, yes. Because it's essentially the same. When you you divide by n. So I want to finish with a last statement. I have 3 more theorems, but I will cite only one. Okay, you will need to check the paper for the remaining one. But I want to give you this one because it makes another link with Carey, which I like a lot. I think I have enough space. So, for a factor map. So this is also from part 2 paper. And this will allow us to make a link with the previous talk, so thanks to Guillaume again, because something similar happens with these tiles. So I define the vector 0, minus 1, 1, and I'm going to do the scalar product of this vector times the vector in Vn. But I know that Vn 0, 0, and plus 1 is not necessary. So in the remaining vector in Vn, I know that the scalar product is always between 0 and n. Because that's the only vector for which the scalar product with d is n plus 1. Okay, so you define the map phi n from omega n to the torus, to the 2 torus, as follows. So you have W, you will map it to the limit of the averages. As we have seen in the previous talk, two-sided around the origin of length 2k plus 1. So I going from minus k to k, and here I define a vector. We'll start with the bottom entry. So you will do the scalar product of d divided by n, so this will give you a value between 0 and 1, of the entries of the vector, the top label of the Wang tiles at position I0. So when I changes, this is a row of tiles, okay? And you're looking at the top values here. Sorry, I see. And then you do the same for the right color of the column at the origin. And this is, okay, I will say it in words because I have 0 minute remaining. It's an almost one-to-one factor map, so it's continuous and onto, satisfying the fact that it commutes with the action Rn defined by rotating by beta horizontally and rotating vertically by beta. And also such that if you apply it on C defined by xy, you recover xy. Yes, I will write it down. Sorry, I will. So this is an almost one-to-one factor map, satisfying phi n sigma k, where this is the shift. So Rn k for n. So this is for every k vector in Z2, and the map is the following. So it's a Z2 action on the torus, where k is a vector, x is a vector. You map it to 1 plus a matrix times x, but the matrix here is the identity times beta. So I can just write beta. Okay. So it's a horizontal translation by beta and a vertical translation by beta. And the part 5, which I don't speak about, is that there are equations satisfied by their tiles and the boundary of their rectangular tilings, but I'm not able to use these to prove non-periodicity. So the initial question remains open, even with those equations. I'm done.
Questions?
What you've done is you've come up with a map from at least some set of configurations with these Wang tiles to the product of two Sturmian sequences. I mean, and do you have any sense of how close that map is to being one-to-one and onto? I mean, basically, you've got the map going down that you know, how close is that to being one-to-one? And then you've got the map going the other way that you know how to create a configuration that looks Sturmian.
Yes, yes.
And how close is that to being onto? And even if you don't have proofs, if you have some intuition that you can share, that would be great.
Yeah, I think we are very close, and we cannot be closer, I think. So one thing I should say here is that since omega n is minimal, already you have this, right? So if you take some configuration, for instance, the one starting with at the origin, and then you shift it by some amount, and you take the topological closure, then you get everything, right? So this explains everything. Like Sturmian sequences, like you have one, you know everything, because it's minimal. And then we need to answer the question with this. So because of the symmetry, so this is the partition for the right color. but the top color will be the symmetric image of that by the diagonal. So you do have two partitions. When you do the refinement of the two partition, you get something like that. 1, 2, 3, 4, 5, 6, 7. So you see the 7 junction tiles are here. The n square tiles will be here. And here you will have the green, blue, and yellow tiles, horizontal and vertical. So the places where, like if you take a generic point here, it's 1-to-1. But if you take a point which falls on a line, there's two ways of seeing it, either as a limit of friends from the left or limits of friends from the right. So those on lines, or those such as the orbit under the Z2 action falls on a line, this is not 1-to-1. And the last point is if you are in the orbit of the origin, then you are 8-to-1. But I don't think you can do better than that.
Question?
I have actually a related question. So if you would start from the direct product of, say, 2 Fibonacci's, right? Yeah. In the self-similar, I mean, now in the geometrically self-similar version, then yes, you actually have 4 blocks that make the tiling. A small square, a big square, and 2 rectangles. That is exactly your n times n, n plus 1 times n plus yes, 1, and so on. Yeah, those 4, right? But the point now is, I think, in 1 dimension, you can't have perfect local rules, but in 2 dimensions, for this inflation, you can. And I have sort of said the impression that the way you code it is actually equivalent to adding some non-local information to have perfect local rules, or maybe go a step in that direction. And that would also explain these 2-to-1 and 4-to-1 and 8-to-1. I mean, the same happens in, that's not the same, but a similar phenomenon happens in Ammann-Benker. The original, the undecorated Ammann-Benker, yeah, does not have perfect local rules. When you want to have them, let's say by the Moses-Goodman-Strauss construction done in optimal way, you have this cover of it that's 1-to-1 on generic elements, but it's multiple to 1 depending on the symmetry points on some of the others, because you've added some information. So if I'm not wrong, then I think you might try to nail this into finding whether you have actually encoded by this perfect local rules for those direct product tilings.
Yeah,
which are shape changes in the sense of Lorenzo from the self-similar geometric tilings.
Yes, so let me comment one thing on it. So in 1 dimension, the substitution which is involved is that one. So for every n, you take this in 1 dimension horizontally, and then you do the direct product of it with itself in the 2 orthogonal direction. So if the incidence matrix is related to metallic mean, and if you look at the left eigenvector, it gives you the relative size of the block. So it really gives, you can construct this as a stone inflation, and the work of Moses tells us that for such a substitution over a 4-letter alphabet, there exists a way to see the letters as Wang tiles on which it projects. So this can be seen as an efficient construction where the tile set is only n plus 2 square. Because Moses, I think it gives you a much larger alphabet. So it can be seen as an efficient way of doing it. And yes, the question is whether we can do it in a more general setup. Yes.
So I suggest we continue. So there's a whole week to ask questions for Sébastien, but for now, it would be a pity not to have time to eat this viennoiserie. So we can thank Sébastien again.
Sure.